Hello. In these videos, in this section, we are going to talk about how we can approximate functions with polynomials. And reasoning for this is, recall in the last section of videos, we saw that we can use power series to approximate functions. In particular, we saw that the function 1 over 1 minus x was the same as the power series from 0 to n, or 0 to infinity, of x to the n. We worked a lot with this function in the last set of videos, which we said was equal to the power series n equals 0 to infinity of x to the n for the absolute value of x being less than 1. This function gave us a lot we could do. We found things about natural log and things about arctan. But what if we're just given a generic function? Is there a way to find this series that goes with it? So that is kind of the goal we're working towards. So first, suppose we have some function f of x. We want to approximate f of x near a point x equals a. So we have a function, be any old function. And then we have some point x equals a, and we want to approximate near that point. Well, in Calc 1, we were given a method to do this. And that was the linear approximation. We can make a linear approximation near this point of the point a at f of a. And how we do this is we use the equation of a line. Equation of a line being y minus y1 equals m, x minus x1. y1 and x1 being our point a, f of a, and then m being the slope. Well, the slope of a tangent line is the derivative. So this line is really y minus f of a is equal to f prime of a, x minus a. And if we solve for y, we get y equals f prime of a, x minus a, plus f of a. The slight rearrangement, this is also y equals f of a plus f prime of a, x minus a. And if you recall from power series, this might generally be looking similar to something we wrote out in the power series section. And I will draw us back to that similarity a little bit later. But in Calc 1, we had this approximation of a function by using a line. So let's review that. Consider f of x equals e to the x. And I want to find the linear approximation of this function. Let's try that picture again. At the point x equals 0. So I want to approximate x equals 0. So I want to find the equation of this tangent line. Well, we know that y equals f of a plus f prime of a, x minus a. saying at x equals 0 is saying a is 0. And my function is e to the x. So a equals 0, f of a, or f of 0, equals e to the 0, which is 1, and the derivative of e to the x is e to the x. So the derivative at 0, e to the 0, is still 1. So filling in that information, we have this line being y equals 1 plus 1 times x minus 0, or 1 plus x. There's the approximation. However, it's an approximation that's decent when we're really close to 0. But as we get farther from 0, like if we're looking out at whatever this point is here, the function and our line are really far from each other. So it's become a really poor approximation. So the farther we get from that center, the worse that approximation of the linear is. So the question arises, how could I make a better approximation? Well, a better approximation would be something that has more terms to it. Right now, we only have 2 terms, 1 plus x, just a line. But we know a quadratic would have a bit of a curve to it. So it would follow the approximation of e to the x, or it would follow the graph of e to the x, a little bit better for a little bit longer. And then a cubic would be even better. A quartic, even better. How do I make a better approximation? I want more terms. Or another way of phrasing that would be a higher degree polynomial. Because right now we can approximate with a first degree, but if I had a higher degree polynomial, that would be better. So, answering that question, how can we determine the equation of an nth degree polynomial that will approximate a function? We are going to go back and use this idea of power series. So, a power series can approximate, represent, equal a function on a certain interval, but a power series can equal a function. So f of x equals a power series, n equals 0 to infinity of c sub n x minus a to the n. And this is what we are looking at in that power series section. Well, writing out a few of these terms, f of x would then be equal to c sub 0, x minus a to the 0 is 1, so I'm not going to write x minus a to the 0, plus c sub 1, x minus a to the first, plus c sub 2, x minus a squared, plus c sub 3, x minus a cubed, plus c sub 4, x minus a to the fourth, and so on. Well, I want to know what these coefficients are, or some way to find these coefficients. Right now, they're just any number. They could be any number at all. I know what those numbers are. So, one quick way is actually plugging in that center A, because when I plug in that center A, then any x minus a is 0. Meaning f of a is just c sub 0. Okay, so I found that 0 coefficient, my constant. How can we find the rest of these coefficients? Well, let's take the derivative. When I take the derivative of f, c sub 0 is a number, so it goes to 0. But then the derivative of c sub 1 is being multiplied by a linear. The derivative of c sub 1 x minus a is just c sub 1. The derivative of c sub 2 times x minus a squared is 2c sub 2 x minus a to the first by the power rule and chain rule, technically. The derivative of the next term is 3 times c sub 3 x minus a squared by the power rule. And we'd have 4c sub 4 x minus a cubed, and so on. What happens when we plug in a to the derivative? The same thing. That will become 0, that will become 0, that will become 0. All that's left is the first coefficient. Let's keep repeating this pattern. Take the second derivative. The derivative of a number is 0. So when I take the derivative of 2 times c sub 2 x minus a to the first by the power rule, this will become 2 times 1 times c sub 2 x minus, the x minus a goes to 0. Well, the exponent becomes 0, so that goes to 1. Plus, then this term by the power rule will become 3 times 2 c3 x minus a to the first plus 4 times 3 c4 x minus a squared, and I'm going to add on another term. The next one would be 5 times 4 c sub 5 x minus a cubed. And continue. Repeating the pattern. If I plug in a to the second derivative, anything with an x minus a becomes 0. So I'm left with 2c2 as the second derivative of a. We might think we're seeing a pattern, but you need to see maybe a couple more rows. Doing this again, 2c2, when we take the derivative of that, becomes 0. Taking the derivative of 3 times 2c3, x minus a to the first, becomes 3 times 2 times 1 c3, x minus a to the 0, plus then this next term becomes 4 times 3 times 2 c4 x minus a to the first, plus 5 times 4 times 3 c5 x minus a squared, and so on. Plugging in a, that's 0, and that is 0, and everything else is 0, making the third derivative at a 3 times 2 times 1 c3. I'm going to see one more to see if there's a really nice way to write this. So the fourth derivative at x, first term becomes 0. The next term will become 4 times 3 times 2 times 1 c4 plus 5 times 4 times 3 times 2 c5 x minus a to the first. I'm going to add on another term of what that would have looked like. It would be 6 times 5 times 4 times 3 c6 x minus a squared. Plugging in a, the fourth derivative at a is 4 times 3 times 2 times 1 C4. You might be seeing this pattern of each time I'm multiplying by the next number up. There is a notation for multiplying consecutive whole numbers together. And that is the factorial notation. 4 times 3 times 2 times 1 is 4 factorial. 3 times 2 times 1 is 3 factorial. 2 times 1 is 2 factorial. 1 times 1 is 1 factorial. And we defined this way back when we defined factorials the first time, but 0 factorial is actually 1 as well. And part of defining it this way is for this process to have a pattern. Meaning, following this pattern, the nth derivative of the function is going to be equal to n factorial times that nth coefficient. Again, we don't know what that nth coefficient is, but that means I can solve for the nth coefficient. C sub n is equal to the nth derivative at a divided by n factorial. Meaning, where this all started was that I can take a function and represent it with a power series. But what are those coefficients? Those coefficients are the nth derivative at a over n factorial. So I can take a function and approximate it with a power series of f of n for a over n factorial x minus a to the n. And that is how I can find our function to approximate. Find the power series that approximates the function. Now, working with a whole infinite power series might not always be the easiest thing to find, but we can find the partial sum, essentially. So the partial sum has its own special name, and it is known as the nth term Taylor polynomial. This is the idea of the partial sum. The nth term Taylor polynomial is, instead of going for the whole power series from n equals 0 to infinity, instead, we're just going for n equals 0 to some term k. Actually, since it's the nth term, the upper bound should be n, the lower bound is k. And this will be approximated by that kth derivative at a over k factorial x minus a to the k. The notation we'll use is p sub n of x, where p sub n of x approximates f of x. And writing out a few of these terms, this will be the function at a over 0 factorial x minus a to the 0, plus the first derivative at a over 1 factorial x minus a to the first, plus the second derivative at a over 2 factorial x minus a squared, and so on until we actually have an ending point, and that is the nth derivative at a over n factorial x minus a to the n. In the next video, we will see an example of using this definition to actually find an approximation for a function.